Hi, my name is Anna, and today I'm going to talk to you about trihybrid line lists, what they are, why we need them, and use CN as an example throughout. Well, what is a line list to begin with? A line list essentially describes a molecule's spectroscopic nature. It is a collection of its energy levels, transition line positions, and transition intensities of that molecule. It's often used to predict absorption spectra or as input to sophisticated models of gaseous environments. The applications for line lists are wide and varied, starting from the likes of fundamental physics and going through a myriad of different applications where you might need the spectroscopy of a small molecule. My personal use is for fundamental physics, where I use it to calculate sensitivities of transitions of small molecules to a variation in the proton to electron mass ratio, but I won't be going through any of that today. What I will be going through is how these line lists come to be and how we might want to optimize these line lists to get the most accurate data. There are three main pathways for this line list data production, and they each have their own advantages and disadvantages. Often you'll see a combination of two different approaches, but very rarely are they all three of them combined. So these three approaches can be broken down into a variational approach, often using duo for diatomic molecules, which is based on solving the Schrodinger equation using potential energy curves. It is also very complete in its nature. We have an experimental approach using Marvel, where experimental transitions are able to produce experimental energy levels. Doesn't give very good information about our intensities, but and is also reliant on how much experimental data is done. And we have our perturbative methodology, which is using experimental data to extract band constants and use model Hamiltonians to derive our energy levels. Very good at interpolating information, but isn't so good at giving you the complete picture. Putting all three of these together, though, we can create a trihybrid line list. What we have to think about with our trihybrid approach is which of the two theoretical approaches, perturbative and variational, will have better energy levels. What we can look at is the residual between our variational method and our experimental method, and our perturbative method and our experimental method, to see which has a lower uncertainty. And we can see from this plot for CN that our perturbative methodology gives us a lower uncertainty for our energy levels. So here we prioritize our perturbative energy levels over our variational energy levels. Putting all our energy levels together with our variational transition data, we have created over 2 million transitions for CN between 0 and 60,000 wave numbers. And we can see here with our cumulative distribution of across intensity that 90% of our strong transitions have experimentally derived energy levels. We can use this to validate and explore where we might need more experimental data. For CN, below 30,000 wave numbers, our line list matches the experimental data very well. We see that above 30,000 to 40,000 wave numbers, we are tending to rely more on our theoretical data than any experimental data available. This can be used to validate other line lists and identify where more experimental data is needed. These are the references that I have used throughout my talk, and I just want to say a big thank you to everyone at UNSW and NSI that has helped me with this along the way. Thanks.